Hello everyone, I am Yasin Arfat Pritom. In this video, I will talk about the history and basic working principles of MOSFET. First, I would love to share some amazing facts about the transistors, followed by a very brief story of the transistors. Then I'll talk about the basic working principles of MOSFET and then explain the characteristics curve of the MOSFET. Then finally, I would love to conclude by sharing some important applications of MOSFETs and some future sophisticated FET structures. So here is a question. Why are devices so interesting? We can have the answer if we think a little bit carefully. Our mobile phone has more computing power than the computers used for the Apollo 11 moon landing. The computer used for Apollo 11 moon landing had 1300 times less processing power than iPhone 5s. Even in 1950s, we had to walk into the computer, but today we can carry a number of computers in our pocket while we walk around. How amazing it is, right? Starting from the vacuum tubes, followed by the inventions of bipolar junction transistors, we are in the era of MOSFET. So what's next after the MOSFET? Different kind of sophisticated FET structures like FinFET, gate-all-around FET, tunnel FET, negative capacitance FET, nanowire FET, etc. are already in the market. Okay, so this is the first planar IC fabricated in 1961, and this is the Intel's first ever integrated circuit named Intel 4004, which was built by using only 2.3K transistors. But today we have billions of transistors in a single chip. So how did we go from 4 transistors per wafer to billions of transistors per wafer? So let's dive into the amazing world of devices by first knowing the operating principles of transistors and MOSFETs. So MOSFET stands for metal oxide field effect transistors. So as per the name suggested, we can assume that we will be discussing about some metals, oxides, and also field effects. So here is a 2D cross sections of a MOSFET. We can see that there are 3 terminals. The first one is the source terminals, which is denoted by S, and then another one is the drain terminals, and then the final one is the gate terminals. Just under this gate electrode, there is a oxide layer. This oxide layer is deposited actually at the top of a substrate. So the drain and the source region are highly doped region, where the substrate region is the moderately doped region. So this gate and oxide can form a channel in the substrate region if the gate terminal is biased appropriately. So the working principle of this MOSFET is very similar to that of a water tap analogy. So how's that working? In a water tap, we can control the water flow by controlling this water tap rotating knob. So the water tap rotating knob is comparable with the gate terminal of a MOSFET. That is, we can control the channel or the flow of carriers through these channels by this gate bias. So here is a N channel and P channel MOSFET symbols, and this is the discrete MOSFET components that we can see in the electronic circuit components shops in the market. This is the 3-dimensional view of a MOSFET structure. Now let's see how the channel is formed in a MOSFET and what happens when we apply a bias or voltage at the gate terminals. Let's assume we applied a positive voltage at the gate terminals. As a result, a positive charge layer will be gathered at the metal and oxide interface. So this positive charge will eventually repulse the holes in the p-type substrate and attract the electrons from this substrate. These electrons will be gathered in the oxide and substrate interface and formed a N-channel layer. So this N-channel will eventually connect the source and the drain and will enable the carriers to flow from the source terminals to the drain terminals through the channel. We can control the channel widths and also the flow of electrons by applying different types of bias in the gate terminals. So we can control actually the current flow in the MOSFET by these gate terminals. So if the channel is N-type, then we can call it the N-type MOSFET, and if the channel is built of P-type carriers, then we call it the P-channel MOSFET. So now let's talk about the IV characteristics or current voltage characteristics of a MOSFET. Specifically, we are interested into the current voltage trend when we apply different types of voltage in the three terminals. So we need two leads in the input terminal and two leads in the output terminals. But in the MOSFET we have three terminals only, so it is obvious that one of the terminals have to be common in both input and the output terminals. Let's assume the common source terminals where source is common in the input terminal and the output terminal. So we can say that gate source voltage is the input voltage of this MOSFET, and then drain source voltage is the output voltage of this MOSFET. So the characteristics curve of a MOSFET can be plotted in a numerous way. For example, if we plot drain current as a function of input voltage while keeping the output voltage constant, we can call it a transfer characteristics curve. And again, if we plot the drain current as a function of output voltage at a fixed input voltage, we can call the characteristics curve as the output characteristics curve. Okay, now let's look into the IV characteristics curve of a resistor and an ideal current source. So in following the Ohm's law, we can see that the IV characteristics curve of a resistor circuit will be a linear line. For higher resistance we will have lower current, and for lower resistance we'll have a higher current. Now in case of an ideal current source, we know that there will be a constant current value irrespective of the applied voltage. That is, we will have a saturated current value which will not change by the change of this voltage. So now our most desired IV characteristics curve of a MOSFET is here. So we can see that there is a linear region as well as there is a saturation region. So we can interpret that if the drain source voltage is small, then the MOSFET will work just like a resistor circuit. And when the drain source voltage is high enough, then the MOSFET will operate just like an ideal current source, that is the saturation region. But in real case, we all know that it's not possible to mimicry or that copy the ideal characteristics curve. There will be some deviation, that is, there will be some small amount of output resistance in the saturation region. That's why the red curve deviates from the ideal one. So this is the complete output characteristics curve of a MOSFET, that is drain current versus the output voltage curve for different input voltages. For each input voltages we will have separate characteristics curve. For each characteristics curve there will be a linear or triad region, that is where the MOSFET will be operating just like a resistor circuit, and there will be also a saturation region where the resistor MOSFETs will try to operate like an ideal ideal current source, but obviously there will be a finite amount of output resistance. There is another region called subthreshold region. So when the gate voltage is small enough is not large enough to turn the devices on, then there will be no current in the MOSFET. So that's when we call that the device is operating in the subthreshold region. So there is another parameter we see, that drain saturation voltage. So this drain saturation voltage is the borderline voltage between the linear region and the saturation region. So when the drain source voltage will be smaller than the saturation voltage, then the MOSFET will be operating in the linear region, and when the drain source voltage will be higher than the saturation voltage, the MOSFET will be operating in the saturation region. And now let's look into the transfer characteristics curve of a MOSFET, so which is the ID versus input voltage curve. So let's take two drain source voltage. One is low drain source voltage and another is high drain source voltage. So the red solid curve is for drain source voltage, and the dotted red line is the transfer characteristics curve of the MOSFET for low drain source voltage. We can also see that there is another voltage in the transfer characteristics curve called the threshold voltage. So the thing is, we need a minimum amount of input voltage to turn on the MOSFET or to turn on the device. This minimum amount of voltage is called the threshold voltage. If we apply input voltage smaller than this voltage, then the device will not be turned on. Okay, so this is a very important parameters in case of a MOSFET. So we can discuss now some applications of the MOSFET. And the MOSFET is applied in both in digital applications and analog applications. In digital electronics, it can be used as a switching circuit or switching device, that is turning on and off a device. And in case of analog electronics, it can be used as an amplifier. So this is the structure. Substrated future structures, FET structures. This is a FinFET, and then there is a nanosheet FET, and then forksheet FET, and after that the complementary FET structure is on the top. So hope to discuss about these sophisticated device structures in any future videos. Thank you.